Thanks for attending this session. So I'm very pleased today to welcome Professor Anna Stuhlmacher from Michigan Technical University. For a bit of background, Anna started as an assistant prof at Michigan Technical University, I think last year.
Yeah, so
Uh,
this fall, yeah.
yeah, that's okay. Well, I guess 2023.
Yes, yeah.
So prior to that, she received a PhD from University of Michigan Ann Arbor and the Bachelor of Engineering from Boston University, all in electrical engineering. So today she'll be presenting about agrivoltaic. So her talk is named Optimizing Dual Axis Solar Panel Operations in Agrivoltaic System and Implication for Power System. So I think it'll be a great opportunity for us to see how optimization methodologies can be used in more than power system, connecting different systems. So thank you very much, Anna, for being here. And the virtual floor is all yours.
All right, well, great. Well, I feel like you got my introduction out of the way, so maybe I can skip that slide. But yes, so this work is done with in collaboration with Johanna Matthew and Pete Seiler, both at the University of Michigan. Feel free to ask questions throughout, as well as questions at the end. I'm kind of structured this to be a little bit shorter of a talk so we can have more of a discussion. So this concept of agrivoltaics, I feel like, is a little bit of a novel, funky concept. And so that might have some opportunity for like an interesting conversation afterwards. Okay, so let's see. Okay, yes. So we kind of already covered this slide, but just a visual representation. So University of Michigan is down here in the lower peninsula of Michigan, and Michigan Tech is up in the upper peninsula, or the thumb of the upper peninsula. So it's about as far as you can get in Michigan while staying in Michigan. And it's also about 3 times more snow than Ann Arbor. So Ann Arbor gets around 58 inches or 1.5 meters, and Houghton gets around 200 inches or 5 meters. So yes, a lot of shoveling so far, but I've been enjoying being at Michigan Tech. Okay, so to provide sort of a motivation or introduction to this concept, I wanted to briefly talk about the clean energy transition, or sort of these goals we have to decarbonize the energy sector and other types of sectors. So in this, we are trying to reduce greenhouse gases and incorporating renewable energy resources. So on the generation side, that's the solar photovoltaic panels and wind turbines, as well as adding storage like batteries and loads like electric vehicles or other types of flexible loads that can shift in time to provide sort of that balance of supply and demand. Okay, so if we're looking at sort of the changes in the power grid, so, generally we have our generation, which is sort of conventional fossil fuel, to our high voltage transmission and lower voltage distribution, out to our demand of our buildings and consumers. And so the sort of big changes we have, it's a lot less linear. I'm still showing it a linear process, but we have our generation that's more from renewable sources, as well as more demand side management with sort of buildings, EVs, batteries, and whatnot. So within this transition, there's a couple of challenges. So the first one is these renewable energy sources are inherently intermittent and uncertain, and so characterizing their power output can be a bit challenging. Just to give a visual example, this plot right here shows the real power output of a solar installation in Arizona. And so we have a nice trend of what this power output is over one day, but looking at sort of the 10-second resolution of this plot is a lot of variability. And so sort of the forecasting in order to balance supply and demand can be challenging. additionally, I feel like this is maybe a little bit less talked about of a challenge, but there's sort of limited land resources when we're adding more of this distributed renewable energy generation. And so if we're about to go put wind turbines or solar panels out, there's sort of a trade-off between using a land for food production and energy production. And so there's some sort of hesitancy or pushback maybe from the agricultural side on using the lands for these purposes. Okay, so this brings me to sort of the concept of the rest of the presentation. And so I just wanted to define it first, since it's a kind of a new area that's emerging, and I think yet to be seen whether it's going to be sort of a worthwhile concept or technology. But this is agrivoltaics. So it has a couple of other names as well. Sometimes it's called like agri-photovoltaics or solar sharing. But agrivoltaics is a mashup of two words, so agriculture and solar photovoltaics. And the concept is placing elevated solar panels over either croplands, grazing pastures, or pollinator fields. So here are some example installations around the world. So we have one in Tucson, Arizona, and then another in Italy, and one in a vineyard in France. So there are some general characteristics of agrivoltaics. So usually they're placed a lot higher off the ground than normal ground-mounted installations. And so this is to let sort of farmers and equipment underneath it to harvest or maintain the crops. Additionally, they're a little bit sparser of a density than normal installations. So if you're looking at that ground coverage ratio, instead of being in that 30 to 50% range, it's more like 13%. Okay. Then if we look under the panels, there's a couple of other sort of characteristics we see in an agrivoltaic system. So the first is usually the plants that are chosen underneath it are a little bit more shade tolerant. So they don't mind being shaded more. So something like lettuce or peppers. Another one is they are generally in warmer climates that maybe you wouldn't think to grow plants in as well, or like less conducive environments. So for example, Arizona's very hot, and so maybe a little extra shading of the plants is not an issue. Okay. So just to kind of give sort of a visual sense of the interactions between crops and a PV system in an agrivoltaic system, I have this little diagram here. So both the crops and the PV system are going to be dependent on the amount of sun they receive. And so we can look at irradiance and insolation. So specifically, the PV system's power output is depending on how much sunlight it receives, and same with the crops. So their growth or their photosynthesis rate is dependent on this. These are going to be dependent upon each other by looking at how much the PV system is shading the crops. And alternatively, maybe like a weaker link is looking at the reflectance of the crops on the PV system. Outside of that, sort of a smaller interaction between them is when you have shading of the PV system over the crops, sort of microclimate under the panel occurs. So it might be a temperature change as well as like a humidity change that you would expect to see. And these can impact both the crops and the PV system. Okay, so looking at an agrivoltaic system, one question you might have is why would we even want to do this? And so there's a couple of different reasons. The first is if we can use sort of the same piece of land for energy and food production, we might be reducing those land use demands that we have. And there might be like a greater acceptance from sort of maybe farmers in this type of case, as well as there's sort of a concept of looking at sort of like the land use efficiency. So if we use the land just for crops, we would have 100% efficiency of producing food and crops. And if we use the land for just solar, maybe we would have that 100% efficiency for producing power. But if we combine them, we might have a greater than 100% sort of efficiency of if we can get value from both the crops and the power produced. Additionally, as sort of like a supplemental motivation, there are some synergistic benefits of when you look at PV panels and crops together. So one example is the crops have evaporation and transpiration sort of characteristics, and this can cool the air around them. And so PV panels are more efficient at cooler temperatures, so maybe you can have a higher PV panel efficiency. Additionally, if you have PV panels over the crops, it might prevent evaporation a little bit more, and so you may have less irrigation needs or need to water the plants less, which could be particularly useful in like a drought-prone area. Okay, so within this area of agrivoltaics, it's a relatively new area, but there's a couple of different areas that we can look at within this problem. So the first is more on the design side. So there's a lot of work being done on the configuration of an agrivoltaic system, where some choices are the spacing between the panels, how high off the ground they are, if it's a fixed tilt PV system, sort of the angle at which they are set, as well as what kind of plants we would put under an agrivoltaic system. There's also the operation side, and so this mainly applies for sort of dynamic PV panels, so single or dual axis panels, and sort of a motivation for this is, so yes, we can get more power produced in a single or dual axis panel system compared to a fixed tilt, but also we can adjust the PV panels to let more sunlight reach the crops at different times in order to make sure that sort of both components of an agrivoltaic system are being met. So we're producing power, but the crops aren't being neglected, and they're getting enough sunlight in order to grow. Okay. So I wanted to provide a little bit of background on the work that has been done in this area. So first, what I want to mention is there was a report out of NREL that looked at some cases that have been more simulation-based, as well as some experimental test cases, and sort of initial results found that you do, in a lot of these cases, have a higher overall land use efficiency. So looking at an agrivoltaic system compared with just having crops or just having a traditional ground-mounted PV installation. Some other work looked at sort of the modeling and simulation of different agrivoltaic systems of different configurations. So looking at the sort of spacing and elevation of these panels. And there's also been some experimental work that looks at what kind of agricultural species we can put, what kind of crops we can put underneath the agrivoltaic, the panels in an agrivoltaic system, and how well do they do. So this is actually that picture from Tucson, Arizona, and they found cases where sort of like the tomatoes or peppers produced more of the vegetable under an agrivoltaic system than when you just have the crops alone, so that the shading was actually helped the plants grow as well as produce power. Okay, so given sort of the literature in this area, there's a couple of areas that haven't been really touched yet. So the first one is almost all of the work in this area looks at fixed tilt PV panels. And so if you want to incorporate some type of dynamic PV panel operation, the operational choices for a single or dual axis panel isn't really addressed. And additionally, while these works provide sort of valuable insight into the benefits and trade-offs in an agrivoltaic system, sort of more formal optimization approaches to determine the best design or operation choices can be sort of important tools. Okay, so that led us to our research question, which is how can we optimize the operation of dynamic solar photovoltaic panels within an agrivoltaic system to maximize value from both the PV system and the crops. And so specifically in this work, we looked at dual axis PV panels, which we could simplify to looking at only a single axis. And so there are a couple challenges with this problem. So the first, if we're considering the sort of value of a PV system and the crops, we need to sort of incorporate both of these models into the problem. But probably the more interesting aspect of this is the timescales of the PV system and the crops. So these are happening at like drastically different timescales of what's important in a PV system and what's important in a crops. So I'll discuss that next. Okay, so very specifically, when we're looking at a PV system, sort of the parameters that we care about or the output we care about is on the seconds sort of range. Whereas when we look at crops, so either their yield at the end of the growing season or their health throughout the season, the smallest time scale we care about is days, going up to months and seasons or potentially years. And so when we're looking at this range of timescales, there's sort of one important concept that kind of links the PV system and the crop system. And so that's on the crop side of when we're modeling crops, their health and their yield. What's an important input into these models is the daily intercepted PAR. So PAR stands for photosynthetically active radiation, and it's the range of solar radiation wavelengths that are useful for plant photosynthesis. And so what this means is the sort of range of sunlight that helps a plant grow. And so sort of the smallest scale we want is the daily intercepted PAR. So given this helped us sort of separate the timescales of this problem, where the daily intercepted PAR is sort of the link between the two problems. So we have the growing season problem, which is our longer, more a problem that's more focused on the crops, and it's going to be for the entire growing season. And then we have a daily operational problem that focuses more on the PV panels. So the growing season problem would have information about sort of the climate forecast over the entire time, over the entire growing season, as well as crop information. And from this, we would set sort of goals or a threshold of how much PAR we'd want in a specific day. And then the daily operational problem would focus more on how do we maximize the power produced by the PV system while still meeting this threshold. So in this talk, I'm going to focus on this daily operational problem for the PV position of a dual axis PV system. Okay, So just taking this component of that diagram, we look at this daily operational problem as an optimization problem that's going to be subject to the PV system and the crop constraints. So in this case, normally if we had a dual axis or single axis PV system, we're going to use a sun tracking algorithm to maximize the power output. So we're going to be having the solar panels follow the sun, so we would have produce as much power as possible. So in this case, we are going to keep the sun tracking algorithm as sort of like the base, and then we're going to determine how much we want to adjust the PV panels away from the sun tracking algorithm. And so this adjustment away from the sun tracking algorithm is what we're using to make sure that that daily PAR threshold is met. And so that daily PAR threshold is determined from that growing season problem. So this will be an input into our operational problem. Okay, so we can take a look at what the general format of this problem would be. So in this case, we are trying to maximize the power output of the PV system within the agrivoltaic system. And so sort of the optimization objective function here is looking at the change in power output from that sun tracking position. So looking at sort of a price, a change in power over a time step. And so in this work, I believe we used 10-minute time steps in the problem. So in this problem, we're solving for the PV panel adjustment away from the sun tracking position. And this is going to be subject to a couple sets of constraints. So first, we have the solar PV panel constraints, as well as given those panel constraints, as well as information about sort of sunlight intensity and position, we're going to evaluate the sort of shading pattern of the PV panel on the crops. And we want to evaluate how much PAR those crops are receiving and make sure it meets that minimum threshold. Okay, so next we can take a look at what those sort of sets of constraints look like. So first we can look at the sort of solar PV side. And so in this case, we have a couple of different inputs. So one is going to be the position of the sun. So this phi sub s is the solar azimuth. So it's the angle between the sun and true south. And then we have this beta sub s, which is going to be the angle between the sun and the local horizon. Another sort of input we have in this problem is the sunlight measurements that we have. So we're looking at direct beam and diffuse irradiance. Okay, so within a two-axis PV panel, I have a sort of a diagram on the right of our two decision variables. So one is going to be the tilt. So specifically, it's going to be the adjustment of the tilt from the sun tracking position, so delta sigma, as well as the azimuth adjustment. So in this case, that delta phi. So that'll be away from the true south position. Okay, so a handful of fun constraints here. The first one, we're looking at the actual PV position, which will be the sum of the sun tracking position and the deviations away from the sun tracking position that we are trying to determine. This next set of two constraints are sort of physical limits on the PV position. So we could only tilt the panels so much or rotate them so much. And so those are the physical design limits. So this constraint relates the position of the sun to the position of the panel. And so we create this theta sub SPV value, which is the incidence angle. So relating the angle that the sun is hitting the PV panel with the angle of the panel. So it'll be the angle from the normal of the PV panel. Okay, this one here is looking at the direct beam and diffuse irradiance, so what's being collected by the panel. And so this will depend upon the position of the panel and the position of the sun, where we use sort of measurements from the site location to get the, as inputs, this direct normal irradiance and the direct horizontal irradiance, or diffuse horizontal irradiance. And then lastly, we can sort of sum up the amount of sunlight collected by the panels and the size of the array and the efficiency of the array to get our power produced. Okay, I'll pause there for a second. Are we all okay? Any questions on this so far?
I have a question.
Yes.
So just to be sure, the sigma PV from the sun tracking is a input, so it's taken as data in the optimization problem. You're not solving in parallel the original sun tracking problem to input. That's something that you can do beforehand, or are you solving it side by side?
Yes, that's a great question. So the sun tracking values, so the sigma and this phi, are going to be dependent upon the sun's position. So in the case where you're trying to maximize the direct beam irradiance, it would be equal to sort of these values here. So it'll be just dependent on them. So if you have an input of where the sun is, you know where you'd want to sort of angle your panels.
So it's a relatively easy calculation. It doesn't need a complex maximization on its own.
Right. It's just a function of these values here.
Thank you.
Mm-hmm. Okay, awesome. Okay, so then we can head to the crop side for the second part of this problem. And so here we're going to have some similar inputs in the sort of sun position and the amount of sunlight and sunlight intensity that we have. The sort of only change is this crop side is going to be dependent on the PV panel position. Outside of that, we also have a PAR threshold, like a minimum threshold that we want to meet so that the crops over the entire day have a certain amount of sunlight that they receive. Okay, so a little bit less constraints on this side, or I kind of hide them all under this function here that I'll talk about. But first, there's a certain percentage, certain range of wavelengths that's important for the crop growth. And so if we look at the total like global horizontal irradiance, we can calculate what the total PAR is available if we had no solar panels blocking the crops. The second calculation is to relate the total PAR to the amount of PAR the crops actually receive. And so we look at it on average over a field, but we could also look at it over smaller spatial resolution. But in this case, we're looking at the percentage of the field that is shaded. And so this is this function here. So SF is the shading factor, and it's dependent upon our choices of the PV panel position. So this includes a lot of trig constraints where we're looking at the vertices of the panels and the position of the sun to see where the shading on the field would be. And I'll talk a little bit more about that on the next slide, I believe. Okay. And then lastly, we have the sort of PAR the crop is receiving at every time period. And then over our sort of time horizon of 1 day, we want to make sure it's greater than the PAR threshold. Yes. And then I guess to describe this figure, because maybe it looks a little weird, this is a plot of just looking at an overhead view of a field, and the blue squares are the overhead view of the panels, and the gray squares, just a little bit to the left of them, are the overhead view of the shading patterns. And so we created just sort of a code that looks at how that shading patterns change throughout the day. So this is a relatively, the sun is high in the sky in this case, and there's not a really wide shading pattern. Okay, and so the problem that we have with all those cosines and sines and the shading factor is non-convex. And so we looked at ways to reformulate this problem and get sort of a base case. So the first thing we did was redefine some variables and use some trig properties. So in our problem, we had a lot of these cosine and sine of the tilt deviation or tilt adjustment, which we replaced with these x and y variables and ensured that x squared plus y squared equals 1, which this is a constraint we relax into an inequality and evaluate afterwards to see how exact it is. And then lastly, that removes a lot of the cosines and sines, but we still have some non-convex constraints with the shading factor. And so this is actually something we approximate in this problem. So we looked at deviations in the shading factor with respect to the cosine of a tilt angle deviation. And we found that it is pretty strongly linear for sort of the small sort of deviations that we were looking at in this problem. And so we approximated the shading factor as a linear approximation in this problem, which is also something we look at later to see how realistic that is. So given this problem, once we relax this, becomes a convex second order cone problem. Okay, so I'll next go on to the case study. So in this, it's all sort of optimization and computer-based, but we pulled in data for a specific location in Michigan. So looking at the Ann Arbor area, we sort of maybe interesting part of this is we looked at the ground coverage ratio, or a ratio of PV to field surface area of around 13%, which is sort of in line with what current agrivoltaic installations use. Outside of that, we pulled historical data from the area. So this is NREL's National Solar Radiation Database, as well as pulled in inputs on what the solar position would be from the PVlib package in Python. So the last sort of component of the sort of case study inputs is looking at the crop parameters and how we set the PAR threshold. So in this work, we said that we're looking at lettuce underneath the crops. And so we used some numbers that are associated with lettuce in this case. So one sort of crop-related modeling parameter that we needed was the light saturation point. So if you think of a plant and sort of the sunlight intensity it receives, you're going to see that the photosynthesis rate, which determines how much it's growing, increases with more sunlight intensity up until a point. And after that point, it starts decreasing. So the photosynthesis rate starts going down because it's receiving too much sun and it's unable to handle it. So that point where it's at its maximum is the light saturation point. And so, normally this PAR threshold would be set by the growing season problem. But in this case, we looked at the percentage of the day that the crop is at its light saturation point. And so in this case, C would be a value between 0 and 1 of how often it's at this light saturation point in order to get the PAR threshold. Okay. So to just show some results from this work, so this is, I guess, very sort of preliminary work in this area, which I just wanted to make a note of. And so I think it brings in some interesting sort of future work by looking at some of these cases. But this table shows our approach of looking at varying percentages of the light saturation point from sort of 80 to 88% of the day, as well as looking at two other cases. So one case where we only have crops and no solar panels, and a case where it's just the solar panels and we're using the sun tracking algorithm to maximize the power production. So in this table, the first column here is the daily intercepted PAR, and the second column is the energy produced from this small scale solar system. Okay, so the sort of first thing that's that I wanted to point out, and this may be sort of intuitive, but as the daily intercepted PAR increases, we're going to have a decrease in energy generation. So as we're adjusting the panels away from the sun tracking position, we're going to be producing less energy. And so this happens as we increase the C value. So as we increase our PAR threshold, we're going to need to have more daily intercepted PAR reaching the crops. And so because of this, we have our daily optimization problem, adjusting the PV panels away from that sun tracking position to reach higher levels of PAR. The second thing I wanted to point out is as we increase C, we see this sort of increase in PAR to meet the PAR threshold. And we see kind of a very dramatic change in the energy produced. I think this is motivation to look at if we have a dynamic PV system, maybe we don't need to stick to having that PV field surface area ratio or the ground coverage ratio being equal to that 13%. Perhaps we could have the PV system a lot more dense in an agrivoltaic system, since we can adjust the panels to let through more sunlight, but we can capture more sunlight collected on the PV panels in a dynamic system. And then sort of just a last result I wanted to sort of point out was looking at how appropriate the shading factor approximation was. And so in this case, this is looking over 1 day, where the red triangle is the approximated value, and the blue square is the actual value for what that shading factor is. And so one thing that we can see here is that for most of the day, the shading factor approximation is very close to the actual shading factor, but we do see sort of a slight worse performance in the first hour of the day and the last hour of the day. But this may not be as important in reality, since there's sort of less sunlight in the morning and evening hours compared with sort of midday hours. And so it's once we look at the irradiance magnitudes, the sort of errors in the shading factor approximation are less significant. Okay. And so just to provide some concluding remarks. So in this work, we formulated sort of a daily operational PV problem so that determines the dual axis PV panel position to meet that crop PAR threshold. And so that's going to be used in that short-term problem as a proxy for the crop health. And in this case, we want to sort of meet those crop thresholds while maximizing the power generated by the PV panels. And then in this work, we showed how we can adjust the PV panels away from the sun tracking position to meet the crop PAR needs. But I think there's also sort of a motivation for in the future looking at higher densities of the agrivoltaic system or ground coverage ratios to more fully sort of explore the trade-offs between these two systems. And then lastly, if we take this from a power system perspective, normal sort of ground-mounted solar installation will have sort of that characteristic I showed on one of those first slides of the PV output. But if we're using the panels to adjust away from that sun tracking position, we may see very different characteristics of a power output from an agrivoltaic system. And so keeping that in mind as we sort of look at sort of the power produced in these cases. So a couple of future directions. One would be including sort of the growing season problem into the formulation, as well as sort of evaluating sort of the exactness of our sort of relaxations and approximations a little bit more, as well as the impact of uncertainty on the agrivoltaic system in terms of crop health and power output. And yes, so I guess if you have any questions, that's sort of the end of my talk. The code is available on GitHub. And so this is a paper that's related to the HICS conference at the beginning of January.